Hello, I'm Sandra Chapman, and with my co-authors Dave Stainforth and Nick Watkins, I'd like to tell you about our paper, Limits to the Quantification of Local Climate Change, which is in Environmental Research Letters.
The focus of climate change science and policy has shifted from global to local. Local changes, particularly in extremes and at user-specific thresholds, influence both practical planning, adaptation, and individuals' perceptions, which ultimately drive mitigation policy. Today's core challenge of climate science is to understand how global change arises from and drives changes at small spatial scales. A key starting point, which we address in our paper, is to quantify the observed changes in distribution at local scales. Precipitation is particularly challenging because we are interested in the tails of what are often heavier-tailed distributions, and because user requirements demand flexible approaches which quantify different types of hydrological vulnerability and address local factors. Here we discuss methodology which maintains the flexibility to provide information at different thresholds for different downstream users, both scientists and decision makers. While previous studies have analysed changes in regional and local precipitation distribution within models, often using dynamical or statistical downscaling, the interpretation of model assessments such as CMIP5 must account for the degree to which such models can reproduce the observed local changes in distribution. Whether one's aim is to quantify and understand observed changes directly or to interpret models in terms of real-world behaviour, a key question is therefore, to what extent can changes in local climatic distributions be quantified given the limited length time series available? This is the question addressed by our paper.
First of all, let's consider the different ways in which the distribution of rainfall at a given location can change. If we have a histogram of daily rainfall observations over a season, we may be interested in either the likelihood of, say, 10mm rainfall in one day, or the summed up amount of rain that falls on intense days, say wetter than a threshold 10mm. Now say the distribution changes so that heavier rain days become more severe. Say a 10mm day becomes a 15mm day, and more rain falls on intense days. This can happen in several different ways. First of all, the mean can increase, so the whole distribution just shifts to wetter days. Alternatively, there's more rain on all types of rainy days in the season. This involves a change in the higher moments such as the variance and skew, as well as the mean. Or there can be the same amount of rainfall overall, but it now falls on more intense days, and the less intense days are drier. In our paper, we propose 4 different parameters to tell these different scenarios apart.
For adaptation, we need to resolve these changes in detail, both geographically and within the distribution. The reliability of climate models at these local scales is a source of continuing scientific debate, but can we do this just using the data? That is, can we extract such information from observations given the fundamental constraints of the data? There are only about 90 daily observations in a season, and geographically widespread observations in many cases only go back to the middle of the 20th century. Let's look at the effect of these constraints for the last case Sandra talked about, the same amount of rain in the season, but now falling on more intense days. Let's just look at 2 plots of how things can change. At the top here, we have the change in daily rainfall, so a 25mm day becomes a 30mm day. At the bottom, we have the change in rainfall summed over the intense rain days. These plots demonstrate what a change could look like if we knew the underlying climatic distribution in each season of each year almost perfectly. But with only 90 days in a season, we don't. To get decent statistics, we need to aggregate at least 9 consecutive years. And since the data we use is only available from 1950, we can only make about 10 estimates of how things are changing over a 45-year period. Here is a rough idea of what these 10 estimates look like. Although there is a lot of variability, the change can still be resolved.
We can estimate these changes locally and use them to plot the changes as maps, and we have done this for the EOBS precipitation dataset, which runs from 1950. At the top we have the change in daily rainfall, and at the bottom the change in rainfall summed over the more intense days. As we move through the distribution, looking at progressively wetter days, we can see how detailed changes play out. In Scotland, for instance, the total precipitation on heavy rainfall days in winter has increased by more than 50%. In southwest France, there is a reduction at all levels of rainfall. These are conservative estimates. We plotted the smallest change of our 10 samples here.
To sum up then, we present new methods to extract solely from the data how precipitation is changing locally, both geographically and within the distribution. Our methods estimate uncertainties direct from the data. In some locations and at some levels of precipitation, clear changes can be discerned from the data. At others, we can see there is clearly no change or that the change is highly uncertain. These results are important for the presentation of scientific data by climate services as a benchmark requirement for models which are used to provide projections on local scales, and for process-based climate and impacts research to understand local modulation of synoptic and global scale climate. They are a critical foundation for adaptation planning and for the scientific provision of locally relevant information about future climate. Thank you for watching.